Chapter 7, Section 1 talks about integrals as net change. And to start with that, we're just going to look at a particle position function. And they give it to us as a rate of change, where ds over dt is equal to velocity of t, which is equal to t squared minus 8 over t plus 1 squared. The question is, if we've got this velocity of a particle moving along a horizontal s-axis from 0 to 5, describe what that motion would be. And so when we're talking about the motion of this particular particle, remember you're moving kind of to the when you're under the x-axis, you're moving one direction. Okay, so if you're down here, remember we're going to say that we're moving left or away. And if we're above the x-axis, we're going to say that we're moving toward or to the right. Okay, and just think about it as a number line. If you're below, if you move to the left of a number line, you're moving into negative numbers. If you're moving to the right of the number line, you're moving into positive numbers. So describe the motion of this particle. And basically what we know is we started with a velocity of 0 because that's where our initial time is. So we would say at v0, and we could put 0 in there for t, and we're going to get negative 8. So we start off at a position of negative 8, and since this is a velocity function, we would say this is negative 8 centimeters a second. Okay, and it's moving to the left, so it's coming from the left-hand side. Okay. And then as the particle follows the graph and moves up and to the right, we cross the x-axis. And when we cross that x-axis, that's a big deal because now that's a change in our position. Okay? So what happens is when we hit to that x-intercept, we no longer are moving left. So we're slowing down, we're moving left. We're slowing down as we move left. We're slowing down our left-hand movement. And then once we get here to this red dot, now we're moving right. Okay? Now we're moving right and we're speeding up. Okay? And we can try and figure out about where that x-intercept is. You can graph it and look at a graph, but it's around a time equal to 1.25 seconds. Okay, it's around a time equal to 1.25 seconds. So what happens here? The velocity is 0. Zero centimeters per second. And then what happens after we cross that point of time equals 1.25? Now we are moving to the right. Okay, so when we're larger than 1.25 seconds, now we're moving to the right. And not only are we moving to the right, we can look at our end time, our velocity at 5 seconds. And what you'll do is you'll just plug in 5 for the t. So I'm going to have 25, which is 5 squared, minus 8 over 36. And when you punch this into your calculator, you get about 24.8 centimeters a second for velocity moving to the right. Okay, so what if we take this same particle now and we go, all right, instead of actually starting out at a position of negative 8, we're going to start out at 9, where our initial position is 9. So what if we start there, what is the position of the particle 1 second later? And when you're working a problem that's like this, what we need to understand is that our position, when we have, let's go with blue here. When t is equal to 1, that's the position that we want to know. So we want to know s of 1. All right. But when t is equal to 1, what we're also saying is we're going to take that initial position. So we're looking at s of 0. Okay. Plus however far we went, or the displacement, displacement, um, to get to 1 second. So how far did we actually move in 1 second? So for this guy, we want to know how far we went from when t equals 0 to t equals 1. Okay? And that's the change in the position. That's what the displacement is. And in order to find displacement, it's an integral. Because remember, an integral is the amount of distance that you have covered. So that's going to help us out here with displacement. And we're looking at an integral. And on this particular guy, we're looking at an integral from 0 to 1 because we want to know how far we went from 0 to 1. And what do? We're looking at that over time. So what's changing? Time. What isn't changing? My velocity function. So to find out that 1 second displacement, we would look at this integral right here. So let's take this guy and sort it out. The displacement's going to be from 0 to 1 of 8 over, well, let's see, t squared, I guess, minus t squared minus 8 over t plus 1 squared dt. Okay, we just want to integrate this, and then we want to look at it from 0 to 1. All right, and so how far are we going to displace? Well, we're going to have t cubed over 3. All right, and then plus, and remember, if I settle up a little u substitution over here, if I let u equal t plus 1, then du is equal to 1 dt. So there's no extra pieces running around there. So basically, what I'm integrating is 8 over u squared, which is the same thing as integrating 8u to the negative 2. Okay? So what I'm going to end up with is 8 over t plus 1. And it's going to be a plus because of that negative guy right here. Keep in mind this is going to be 8u to the negative 1 over negative 1. And so we're evaluating this integral from 0 to 1. And when you evaluate this integral from 0 to 1, you're going to end up with a stop minus a start. So that's going to be, 1/3 plus 8 over 2. There's my stop minus my start, which is going to be 0 over 3 plus 8 over 1. Okay? Which is going to end up giving us a fraction of negative 11/3. So this is my displacement. And in order to figure out how far I traveled, then I'm just going to follow my equation here. My initial position plus my displacement. So initial position, which is 9, plus displacement, which is negative 11/3. That's going to get me how far my particle actually traveled, which is going to be 16/3. So it's not a terrible process to go through. Well, what about if we traveled for 5 seconds? What would we work? Well, we would work the integral then from 0 to 5, okay, of t squared minus 8 over t plus 1 squared dt. And that's going to give us the same thing that we just had in blue, which is going to be t cubed over 3 plus 8 over t plus 1. And we're going to evaluate this now not from 0 to 1, but for the full 5 seconds. And so now that gives us a little bit different numbers. So we're going to have 125 over 3 plus 8 over 6 minus the 0 part, which is just going to be 0 over 3 plus 8 over 1. And when you work that guy out, you should get 35. And so now if we want total displacement for this guy, we would do the same thing. Initial position plus the displacement. So 9 plus 35, and that'll tell us how far our particle traveled, which should be 44 total units. Okay, so the biggie for this guy is that your final position is equal to your initial position initial plus displacement. So if we wanted to sort this out for 10 seconds or 20 seconds or 2.5 seconds, we could do any of those or all of those. All right, now the question is, what is the total distance traveled instead of just where has the particle moved to, or how far has the particle moved? Like, what is the total distance traveled? And what this is going to do is take out the negative parts of this, because when you look at total distance, what you're going to look at is the integral from A to B, which is your start and stop. But you're going to look at the absolute value of that velocity function. The absolute value of that. The reason we want the absolute value of that is because distance is always positive. Okay, you're always going to drive forward. And so then what we can do is, if we want to know how far this particle traveled from 0 to 5, then what we would do is we just run that integral again from 0 to 5. So we're going to go from 0 to 5, and we're going to do the integral of the absolute value of t squared minus 8 over t plus 1 squared dt. And here's what I would recommend. Punch this into your calculator. We can do that now. You've got a definite integral. Your technology can help you. If you want to do it old school way, that's fine. But just go ahead and punch this guy in, and what you're going to end up with is approximately 42.59 units. Okay, so instead of just being told, where we end up as a final position, we're actually going to look at exactly how far this particle traveled. A car is moving with an initial velocity of 5 miles per hour, accelerates at the rate of 2.4 t miles per hour per second for 8 seconds. How fast is the car going when the 8 seconds are up? This is very similar to the first problem that we did. And in fact, we're going to look at the integral. We're starting at a time of 0, and we're going to go to a time of 8 seconds. And the function that we're really interested in is at 2.4 t. And the acceleration is changing over time, so we're going to look at dt. And again, you can punch this into your calculator or not. You've got technology. It's a great thing to have, and if you don't, you're going to end up with 2.4 t squared over 2, evaluated from 0 to 8. And if you do punch it in, either way you go, you're going to end up at 76.8 miles per hour. Okay, that's how fast the car is going when the 8 seconds are up. Okay, but we started with 5 miles per hour already in there, so we're going to take the 76.8 and add 5 miles per hour. And that'll give us our final answer of how fast our car is going. We started off at 5 miles per hour. We accelerated to 76.8 miles per hour. So how fast were we, we accelerated that far. How fast are we going all together? And it should be 81.8 miles per hour. Okay. Well, how far did the car travel during that time? And so what we want to know is the velocity of the car, because to find that distance, you might remember from the previous slide, we need to take the integral from a to b of the absolute value of the velocity function. Okay, and this is acceleration. This is an acceleration function, not a velocity function. So how can I figure out the velocity? I integrate acceleration. Okay, remember that when you take a derivative from a position, you have velocity. When you take a derivative of velocity, you have acceleration. So this is kind of a two-part process here. Part one is we're going to look at our original guy, which is 5 plus, and then we're going to go from 0 to 8. 0 to t. Actually, we'll use the fundamental theorem of calculus here. And we're going to do this for 2.4. And we're going to use u in this case, du. It's the same thing. It's the same thing, same deal, right here. Okay. And when we do this, we're going to end up with 5 plus 2.4 over 2 times t squared. Okay, and basically what we're doing is we're just going to let u equal t. Okay, that's kind of what's going on here. All right, and so this gives me a velocity. Okay, this gives me a velocity, and once I've got a velocity, then I can integrate that guy to get my total distance. So distance is going to be, total distance is going to be the integral from 0 to 8 of 5 plus 1.2 t squared dt. And in order to get distance, then keep in mind I've got to do absolute values. Okay, and so when I do my absolute values, what I would just recommend is just punch this into your calculator. Use your technology to help you out. You're going to end up with a total distance of 244.8. So when I punch that into my calculator, I get 244.8 miles per hour per seconds. Okay. And we don't usually use miles per hour seconds, and so we would just need to convert this just a little bit, because we usually deal with like miles per hour, not miles per hour per second. So we would take that 244.8, and to convert it to something useful, we would just figure out there's 1 hour and there's 60 minutes. And then there's so 1 hour to 60 minutes, and then 1 hour to 60 seconds. So this is our conversion. Here's our minutes. Here's our seconds. And so then we would punch this in, and we'd find out that our total distance covered is 0.068 of a mile. And that all happened during that 8 seconds of driving. Instead of looking at acceleration and velocity and all of that, we can actually look at the rate of potato consumption in a particular country from 1970 to 1980. And it was modeled by the equation consumption of T over T is 2.2 plus 1.1 to the T power in millions of bushels per year, with T being years, since the beginning of 1970. The question is, how many bushels were consumed from the beginning of 1972 to the end of 1973? So basically, we've got a function up there, this consumption function. That's going to be this guy right here. And the thing that we're really interested in is from year 2 to the end of year 3. So basically, we're going for 2 is less than or equal to t is less than or equal to 4. Okay? That's about what we're looking at because we're starting at the beginning of 72 and ending at the end of 73. Okay? So what's my integral look like? It looks like the integral from 2 to 4 of 2.2 plus 1.1 to the t dt. And again, I would use your calculator to do this. If you want to do it longhand, that's great. That's a good skill to have. But since we're given all the information, we've learned that skill on previous lessons, plugging this thing into your calculator is not such a bad thing. And what you're going to end up with is the number 7.066. And 7.066 is your number. But remember, we're talking about in millions of bushels. So this is 7.066 million bushels of potatoes consumed by a particular country. Alright, now we've got this pump connected to a generator which operates at a varying rate. So the rate is not consistent. And depending on how much power is being drawn from the generator to operate other machinery. So it goes up, it goes down, it's never the same. The rate in gallons per minute at which the pump operates is recorded over 5-minute intervals for 1 hour. How many gallons were pumped during that hour? And it's not quite so easy as adding up the 58, the 68. It's not so easy as that because we have a variance in how consistent it is. So just coming through here and adding up the bottom line won't always work. Now it might sometimes, but we also aren't given a function. So here's what we do know. We know that gallons pumped is equal to the integral from 0 to 60, okay, of our rate function. And that rate function is going to be over time. We're not given a rate function, but we are given a series of points and some information that matches that. So instead of looking at it as an integral now, what we're going to do is we're going to check this guy out with the trapezoid rule. The trapezoid rule. Because this is an easier time to use the trapezoid rule since we aren't given a specific function to work with. And I don't know what I'm spelling here, trapezoid. And so what we're going to do is you're just going to follow that rule, which is going to be the total time it takes, which is 60, divided by 2 times the number of intervals, which is 12, and then times, and don't forget how trapezoid rule works, it's going to be that first guy, plus 2 times the second guy, plus 2 times the third guy, plus 2 times the next guy, and all the way through the problem, all the way till you get towards the end where you're going to have 2 times 60 plus 2 times 63 plus 63. So there's your trapezoid rule, and if you want, I'll tell you, I'll use the big brackets right here, big brackets. So you would just punch this into your calculator, and what you're going to end up with is that this pump has actually pushed through 3,500-ish gallons of material. In 1 hour.